Okay, I assume we're all good.
I can hear you. Sorry.
That's right, cool. Okay, good to know. Yeah, I'm Tom. I'm from Cam School of Mines. I'm also part of the NL4D consortium project. So we've had quite a good few presentations from our group today and also in the previous session last week. I'm going to be talking about using an automated approach to domaining downhole geochemical data in the northern limb. So let's get started. I won't give too much of an introduction to the northern limb or anything else because I think we've already had enough of that. So I'm going to just give a brief introduction to the problem I'm tackling here, and that is how can we automate a particular process of interpreting some downhole information. So in the northern limb, I think it's fair to say within the Platte Reef, certainly there's some uncertainty around how we can usefully subdivide the critical zone or the Platte Reef into useful domains. In the core, there's not a lot of information to see. I think Erin and Kate have been seeing this. They've been out there recently and they talked about this in their talks, that it's quite hard to identify domains from just the core. But when you start looking at the bulk geochemistry, you can pick out some quite useful information. Again, that was shown by Erin and also Kiara in her talk last week. And you can start to generate some geochemical domains that can be correlated between holes. So that process of interpreting, as Kiara did, particularly in this picture is taken from her work, of interpreting putting boundaries between some of these major changes in the downhole mineralogy, that in itself is quite a trivial task. So I think if you gave that problem to any geologist and asked them to start at the top of the hole and a boundary where they see the sort of change in the mineralogy, we would probably all start by putting one there perhaps, and then moving down we might count those changes there. May start to get a bit more problematic as we get into the details, but we might start seeing little things that we could pick out there and there. So that in itself is quite a trivial task. The real challenge, as we know as geologists, is interpreting what these domains mean, correlating them, and working this all together into a sort of a model of formation and mineralization. But I thought the process of actually identifying the boundaries could be an interesting one to try and find an automated way to do this, because we're working with a lot of data in the northern limb. So as I say, why automate this? Broadly speaking, I'd say it's down for two reasons. It's down to the data volume and trying to to work around subjectivity and bias. So as I say, we're working with a lot of data, and the more data you get, the more time consuming it becomes to interpret holes manually. And the more time you spend interpreting the holes, the more reluctant you're going to be to reinterpret those holes should you need to. And then there's the problem of subjectivity. So there's the old adage, if you give the same problem to 5 different geologists, you'll get 5 different answers. And that's arguably a good thing. But if you are wanting a consistent interpretation, but you're working with a team of multiple geologists or geologists over time, as in, geologists from 10 years ago interpreting things in a different way to the geologists working on the same project now, you're going to come into some issues. And then there's this whole concept around an anchoring bias with interpretations where you're more likely to interpret close to your existing interpretation. You're going to be it's quite hard to get away from a particular interpretation once you've been exposed to it. So being able to reinterpret and come up with different models is quite useful. And I think using a bit of a data-driven approach can help us with these things. And I think these 2 points kind of reinforce each other. The more data you have, the more sort of bias you may become and everything like that. So before I go into the method I use to automate the methodology, just a quick word on CIPW normative mineralogy. One of the first steps that I was going to be performing was to calculate the normative mineralogy for a large number of samples. I found there wasn't an existing solution to do this particularly effectively. So I went and wrote the algorithm for CIPW normative mineralogy, or at least a version of it, in Python. And that is now, I worked with Morgan Williams to get that implemented in the Python package Pyrolite, which, if you haven't heard of it, is a really useful package for working with geochemical data. So yeah, you can go and use that algorithm now for free if you install Pyrolite. I can recommend Pyrolite anyway for anything else you want to do. If you're not into Python, I also have made the code available in the form of a web app, which you can find at this address here. And you can just upload your geochemical data and it will spit out your normative mineralogy. So if that's something that you need to do, then give it a go. And if it doesn't work, please please let me know, because yeah, it's my first time making something like that. So after that little plug there, how do we actually automate the process of identifying boundaries and domains? So I started off this by just thinking I could use Kmeans. Kmeans is very useful. We've already seen a few talks just now of the use of it and how it works. So I thought I'll use Kmeans on the centered log ratio transformed normative mineralogy. And this is the result on the right. So each different color is a different cluster. And broadly speaking, I think we can see there's a fairly good comparison to where there's a major change in the mineralogy. One of the sort of issues is that there's some areas of noise, which I think naturally as geologists or humans, or well, geologists are humans, but we'd naturally filter out that noise if we were chunking this into sort of, okay, this is all the same, this is all the same. Whereas the K-means algorithm just considers every sample individually, and so we end up with some noise. So it'd be nice to get rid of that noise. Obviously, some of the noise may be important, depending on the scale of observation, so that's also important, but a lot of it isn't. So is there a method that we can use to both smooth the data across a range of scales and identify boundaries? And it turns out there is. Oh, that's an animation too quick. There's a method that's existed called the continuous wavelet transform. It's a method for identifying boundaries, and it's been worked up into a really nice workflow by June Hill from CSIRO. They call it the data mosaic tool. And I'll quickly try and explain how it works. So the continuous wavelet transform, what is that and how does it work and what does it actually tell us? So if we consider a downhole signal, this could be geochemistry, it could be wireline geophysics, any continuous signal. We take a thing called a wavelet, which is basically just a moving average window with a Gaussian shape, and we slide it along our signal and average over that window, and we weight that average by the shape of the wavelet. We get another signal. Now, if we repeat that for different sizes of wavelet, if we increase the size of wavelet, we'll get an even smoother signal. And we can do this with increasing size of wavelet until we've got a very smooth signal, and we can do it in all scales in between. So we can, yeah, and we can do it continuously, hence the continuous wavelet transform. If we join those together, we end up getting something called a scalogram. Now, is anyone else getting a bit of noise? I'm just going to mute myself or turn off the volume. So if we join these together, we get the scalogram. If we use a particular type of wavelet, we can do something clever where we get a scalogram where the zero values of the scalogram, so in this instance where it's colored white and I've contoured it, they tell us where the inflection points in the signal are. And in other words, an inflection point is a boundary. So we found the locations of our boundaries in our signal. Now, if we use another type of wavelet and derive another scalogram, we can overlay those contours from the first one. And this scalogram tells us the strength of the boundary. So we can extract the values along the contours, and that will tell us the strength of the boundary. Put those two bits of information together, and then we've got something that tells us where a boundary is in our data and how strong relatively that boundary is. And then what June Hill does in her method is she joins them all together to form this this mosaic plot. which can help us interpret. So this is showing us across all scales, different ways of essentially dividing up our data into packages. So at the larger scale, we can divide it up into these three. Going down, we get some more details, but still with sort of large amalgamations of data, until we get the finer scale where it's picking up every single boundary. So how do we actually, what does this actually look like if we apply it to northern limb data? So starting off with our normative mineralogy, we use this for the input into the method. Just to remind you that that's the Kmeans result from earlier on that data. Now, these are the manually interpreted boundaries from Kira's work. And this is the output from the method I just described, the mosaic plot, from which we can see some boundaries. So if I overlay the locations of the manually derived boundaries, we can start to see that on this mosaic plot at sort of a particular scale around here, we see a lot of these boundaries matching up with boundaries picked up using the automated method. So that seems pretty good. There's another way we can compare these results. If we just take our manual domains, the manually interpreted domains, and color them by the most commonly occurring Kmeans value within that domain, and then along a particular scale on the mosaic plot, we can extract what we can term a pseudo log. And you can see it at that scale of observation. If we compare it with our manual interpretation, we've got a very good comparison between the two. There are some mismatches, there's some differences, but overall it's a pretty good interpretation that we've managed to derive automatically. What does this look like if we look at all the wells together? Well, the location of the boundaries I think is good. So if we look at sort of this domain 1 to domain 2 boundary, it's fairly consistent. This well's a bit funny, it comes out quite strange, but so we can ignore that one. But the location of the boundary is fine. But what isn't working so well is the classification of the domains between the wells. So for instance, this domain 2 is not consistent between the boundaries, pretty consistent, I'd say, but the classification of it is not. So that's something that needs to be worked on to improve that. So where am I going to take this next? Well, I've performed it just on 5 holes. I'm now in the process of deploying it across many more. The benefit of it is you can deploy it on many holes quite easily. Once we've got that, we can start looking at things like the spatial correlation of these domains. How do they spatially correlate and relate to each other? I need to investigate some other clustering methods to come across that problem of where there's a mismatch between domains across holes. And finally, I think this is the most important thing. I need to think about what input variable do I want to use into this whole process. So I've showed it using the CIPW normative mineralogy, which is fine. But we could use any number of geochemical variables or ratios. It all depends on what we want to know. Do we want to identify things related to the mineralization, or do we want to identify zones of alteration, or things like that? I think, again, the power of this technique is that we could generate a number of different domains or models by using different inputs, and we can do that all quite rapidly across a large number of holes. And then the hard part is interpreting the results, I guess. So thank you for listening. I'm not sure how I'm doing for time, but if I've got any time, I'm happy to answer questions. And just, thanks to all the colleagues from NL4D project. Thank you.